Welcome to my Tech Talk.
You're tuning in because, well, you want to get a solid handle on Kotlin, and you want to do it efficiently, right?
Yeah.
Without getting totally bogged down.
Yeah, avoiding that information overload, but still getting those aha moments.
Exactly, those key insights that make things click. So we've designed this as your shortcut, really, to understanding what truly matters in Kotlin today.
Our mission for this session is pretty focused. We've got this wealth of information, this reference doc on Kotlin.
Right.
And we're basically going to pull out the essentials, the must-knows, and maybe some surprising bits to give you a clear picture.
And we're not just scratching the surface. I mean, the source material covers a huge range, doesn't it?
Oh, yeah. Everything from, like, compiler options and how Kotlin plays with Gradle,
Okay.
all the way to multi-platform stuff, and, of course, tons of language features.
So let's dive in. Let's really get into what Kotlin's all about.
Sounds good. Let's maybe kick things off with how your Kotlin code actually becomes a running app, the compiler and build process.
Good starting point.
The full details on compiler options are in the docs, naturally. But what's immediately useful for most people is how the Kotlin Gradle plugin streamlines the whole build process.
Okay, this Gradle integration sounds pretty crucial. What are the main benefits it offers?
Well, the big wins are mostly around efficiency. First off, the plugin supports incremental compilation.
Right, I've heard about that.
Think of it this way. Small code change, big project. Gradle with the Kotlin plugin is smart enough to only rebuild what's absolutely necessary.
Ah, okay.
That can seriously slash your build times. We're talking minutes down to seconds sometimes. It's a huge productivity boost.
Definitely.
Plus, it integrates really smoothly with Gradle's build cache and configuration cache features.
This means?
Basically, Gradle remembers the outputs from previous builds. If nothing's changed, it just reuses the old results. So subsequent builds get even faster.
Faster builds, yeah, always a good thing. Now, I saw something about a Kotlin daemon. What's that doing?
They're Kotlin daemon. Yeah, it's kind of like a persistent helper for the compiler. It's a background process that keeps the Kotlin compiler sort of warm, running in memory.
Ah, so it doesn't have to start up every single time.
Exactly. It avoids that startup time, which really adds up, especially in bigger Gradle projects.
Yeah.
The plugin also has some smarts built in for how the compiler actually runs and fallback strategies if, things go wrong. And for people who like to tinker or need to troubleshoot, you can even roll back to an older compiler version or try out the absolute latest language features.
So it's about efficiency, but also giving you options. Got it. Now, K2 compiler and capped were mentioned. What's the significance there?
Right, K2. That's the next generation Kotlin compiler. It's designed for better performance and to enable new language features down the road.
Okay, the future.
And capped. Well, lots of great Java libraries use something called annotation processing. Capped, the Kotlin annotation processing tool, basically acts as a bridge. Yeah, it lets you use those powerful Java annotation processor-based libraries smoothly within your Kotlin projects. And K2 is being integrated with Capped.
How's that going?
It's progressing well. But, with any big transition, if you do hit any snags, you can easily flip back to the older K1 implementation. There's just a simple flag for it in your Gradle.properties file.
Right, a safety net. Good to have.
Exactly. Provides a smoother transition.
Makes sense. What else on the Gradle front should we know about? Anything tricky?
Well, there's this isolated projects feature in the Kotlin Gradle plugin. It's quite clever, actually.
How so?
It helps Gradle build tasks in parallel more effectively and kind of sandboxes different project parts during the build. But in multi-platform projects, which can get pretty complex structurally, you might sometimes run into issues after upgrading Kotlin. It's not common, but if it happens, you can disable this feature with another setting in Gradle.properties.
Okay, so something specific to watch out for with multi-platform.
Yeah, it just highlights that multi-platform sometimes needs special consideration.
Anything else Gradle-related worth noting quickly?
Yeah, a couple of specific points. The way the plugin handles dependencies for Java test fixtures, test utility code, that now aligns perfectly with how Gradle itself does it as of Kotlin 2.0.20, should prevent some weird test setup issues.
Good.
Also, you might occasionally see these Gradle properties with long names like org.gradle.java.com, compile-class path packaging, or kotlin.build.archives task output as friend module.
Right.
They offer really fine-grained control over specific build aspects if you ever need to get that deep into customization.
Okay, power user stuff. Now, incremental compilation itself, you said it's a big win. Has that been getting better too?
Oh, definitely. The new JVM incremental compilation has been the default in Gradle since Kotlin 1.8.20. It's a significant step up in speed.
Nice.
And there's now a more precise way the system backs up compilation task outputs. This helps ensure incremental builds are reliable, even if something hiccups during the process.
Reliability is key.
Absolutely. And it's also important to know that the old way of controlling the compiler execution strategy, using that kotlin.compiler.execution.strategy system property, that's deprecated now, not recommended.
Good to know it's being phased out.
Yeah.
And it seems like we're getting better tools for actually understanding build performance too.
Exactly right. Since Kotlin 1.7.0, you get build reports generated for Kotlin compiler tasks.
Build reports. What do they show?
They can be super helpful. They show how long different parts of the compilation took, help you spot bottlenecks, and figure out why a build might not have been fully incremental. Gives you actual data to work with for optimization.
That sounds incredibly useful, especially for big projects where build times can really drag.
Yeah, it's a great addition.
Any final thoughts on compilation and Gradle before we shift to the language itself? Any breaking changes maybe?
Just a few minor housekeeping things in how Kotlin compile tasks are configured. This source file's extensions input is gone. You use Gradle's standard ways now. The class path property is deprecated, and the output directory, which used to be destination dir, is now consistently called destination directory. Little things, but good to know.
Right, consistency.
And finally, all Kotlin compile tasks now use the library's input for their dependencies. Just keeps things standard.
Okay, that gives us a really solid picture of the build side of things.
Yeah.
Let's switch gears now. Let's get into the core of Kotlin, the language, the syntax. Where's a good place to start?
Let's start at the very top of a Kotlin file. You'll usually see a package definition first.
Standard stuff.
Yep. Followed by any import statements you need to bring in code from elsewhere. And as you probably know, the keyword fun is how you declare a function.
Right, fun. Nice and short. What about variables? I know Kotlin really emphasizes immutability.
That's a cornerstone, yeah. You declare read-only variables assigned once using the val keyword.
Val for value, basically.
Exactly. And for variables that can change, you use var. Kotlin's pretty good at figuring out the type automatically. That's type inference. But you can always specify the type explicitly if you want or need to.
And file naming. Any conventions there?
Yeah. The common practice is to name the .kt file after the main class or interface inside it. Use upper camel case?
What if there isn't one main class?
Good question. If a file has multiple top-level things, just pick a name that describes the contents well, still using upper camel case. Keeps things organized.
Makes sense. Now, functions, I heard they can have expression bodies. What's that?
Yes. If a function's entire body is just a single expression, you can use a shortcut. An equals sign followed by the expression makes it very concise.
Instead of curly braces and a return.
Exactly. And if a function doesn't return anything meaningful like void in other languages, the return type is unit. But you can usually just omit unit entirely. Kotlin cleans it up.
Nice. Okay, what about the fundamental data types, the building blocks?
You've got the usual suspects: int for integers, double for floating point numbers, boolean for true-false, char for single characters, string for text.
Pretty standard.
But Kotlin also adds unsigned integer types: ubyte, ushort, uint, ulong. You spot those literals because they have a u suffix.
Ah, okay. 10u would be an unsigned int.
Precisely. For floats, you use float with an f suffix or double, and Kotlin supports augmented assignment operators too, the shorthands like plus, etc.
Convenient. And working with text, string templates seem like a big feature.
They really are super convenient. They let you embed variables or even complex expressions right inside a string.
How does that look?
Just use a $sign before a variable name, like name, or if it's an expression, wrap it in curly braces like user.age +1.
Much cleaner than endless plus signs for concatenation.
Way cleaner and less arrow-prone too.
Okay, let's talk collections. Arrays, lists, maps. How does Kotlin handle those?
For arrays, you can create them using functions like array with initial values or array of nulls for a fixed size filled with nulls. There's also an array constructor where you provide a lambda to calculate each element's value.
Gotcha.
One key thing about Kotlin arrays: they are invariant.
Invariant. What does that mean practically?
It means an array string is not treated as a subtype of array any. This helps catch potential type errors at compile time rather than runtime.
Ah, type safety. Makes sense. What about other collections like lists and maps?
Kotlin makes a very clear distinction between read-only and mutable collections. For maps, you have map for read-only and mutable map for maps you can change.
And how do you create them?
Usually with helper functions like mapoff for read-only and mutable mapoff for mutable ones, you can get all the keys with the keys property and all the values with values.
What happens if you try to get a key that isn't in a read-only map?
Good question. It simply returns null, doesn't throw an exception.
Okay, important behavior to remember. What about controlling the flow of code? Ifs, loops.
Kotlin has a really powerful when expression. It's like a supercharged switch statement.
How so?
You can use it with a subject, and it checks branches sequentially until one matches. Or you can use it without a subject, just listing Boolean conditions. It executes the branch for the first true condition. Very flexible.
Sounds useful. And loops.
You've got the standard while loop and also the do while loop, which always executes the loop body at least once before checking the condition.
Familiar territory there. Now, functions seem really central in Kotlin. I keep hearing they're first-class citizens. What does that actually let you do?
Being first class means you treat functions just like any other data. You can store a function in a variable.
Okay.
You can pass functions as arguments to other functions. Those are called higher order functions.
Right.
And you can even have functions that return other functions. Kotlin uses function types to represent these.
Function types. What does that syntax look like?
It shows the parameter types in parentheses, then an arrow void, then the return type, like int, string, Boolean.
Got it. And lambda expressions fit in here somehow.
Exactly. Lambdas are a super concise way to write anonymous functions, often used when you need to pass a function as an argument to a higher order function.
They're the bits in curly braces.
That's them. Inside the braces, you list parameters first, if any, then the lambda scan. If the compiler can figure out the types, you can often omit them.
And the return value.
The last expression inside the lambda is automatically the return value. Super neat. And if a lambda is the very last argument in a function call, you can move it outside the parentheses entirely. Makes code really readable, especially for things like configuration blocks.
Ah, that trailing lambda syntax. I've seen that.
Yeah. Kotlin also has function references using the double colon front. It lets you refer to an existing named function, could be top level, local, a class member, an extension, even a constructor or property getter without actually calling it. Useful for passing functions around.
So lots of ways to work with functions as values. What about defining our own types? Classes.
Right, classes. You declare one using the class keyword. A key Kotlin feature is defining properties directly in the primary constructor.
How does that work?
In the class header, you just put val or var before a constructor parameter name, and it automatically becomes a property of the class.
Oh, that saves boilerplate code.
A lot of boilerplate. A class has that primary constructor in the header and can also have secondary constructors defined inside the class body using the constructor keyword. You access properties using the usual dot notation.
Simple enough. What about data class? That seems popular.
Very popular. You use the data class keyword. The compiler then automatically generates useful methods like toString equals, hash code, and a really handy copy method.
Yeah.
Yeah, lets you create a copy of an instance, optionally changing some properties. Great for immutable data structures. Saves you writing all that standard stuff yourself.
Definitely useful. What about sealed class and sealed interface? When do those come into play?
Sealed classes and interfaces are for creating restricted class hierarchies.
Restricted how?
The key thing is, all direct subclasses or implementations must be declared in the same package as the sealed class or interface itself.
Why that restriction?
Because it lets the compiler know all possible subtypes at compile time. This is incredibly powerful when you use a sealed type in a when expression.
Ah, because the compiler can check if you've handled all cases.
Exactly. It can perform exhaustive checks and warn you if you missed a subtype. They're fantastic for modeling things like UI states loading, success, error, or different results of an operation. Makes your code much safer.
Great for state machines and similar patterns.
Got it.
And the object keyword. I know that's for singletons.
Precisely. Declaring object mySingleton creates a single, ready-to-use instance. There's only ever one.
Can objects have data class-like features?
Yes. If you declare it as data object, the compiler adds the toString and other utility methods, just like for a data class. Very useful for simple, constant-like objects.
What about anonymous objects?
You can create unnamed objects on the fly using object design supertype. Their exact type is inferred, and their visibility depends on where you declare them. Useful for quick, one-off implementations of interfaces or classes.
Okay, we've covered classes well. Let's zoom in on properties again. How can we customize how they behave? Getters and setters.
You have full control. You can define custom get and set value methods for any property.
What if you need to access the underlying value inside the getter or setter?
You use the special identifier field. It represents the backing field where the property's value is actually stored.
Can you make the setter private, but the getter public?
Yep, you can specify visibility modifiers, private, protected, etc., on the getter or setter independently.
What about properties that aren't initialized immediately?
For non-nullable properties that you know will be initialized later, for example, in a setup method, you can use the latinate modifier. Avoids having to make them nullable just for initialization.
Are there restrictions on latinate?
Yes, it only works with var properties that are non-nullable and aren't primitive types. And accessing it before initialization throws an exception.
Good to know. Extension properties, like extension functions.
Exactly like extension functions. You can add new properties to existing classes without modifying their code. They don't have backing fields, though. They must define custom getters and optionally setters.
And delegated properties, the by keyword.
Delegation. Very powerful. Using by, you can delegate the getter and setter logic of a property to another helper object. That object needs to implement specific get value and set value methods, or just get value for a val. Allows for reusable property behaviors like lazy initialization, observable properties, storing properties in a map, etc.
Okay, that's a lot of control over properties. Now, functional interfaces and type aliases, they seem related. What's the difference?
Good question. They can seem similar. A typelias, using the typelias keyword, is just a new name for an existing type. It doesn't create a distinct type.
Just an alias, like the name suggests.
Right. Purely for readability. A functional interface, declared with fun interface, however, does create a new unique type.
Why is that distinction important?
Because you can define extension functions specifically for that functional interface type, which you couldn't do for a plain function type or a type alias of one. It gives you more type safety and extensibility options.
Got it. New type versus just a new name. What about inline functions? We mentioned them briefly with build performance, but how do they work in the language?
Right, inline. When you mark a function inline, the compiler essentially replaces the function call with the actual code inside the function, right there at the call site.
It copies the code in.
Pretty much. This avoids the overhead of a normal function call, like creating a stack frame. Good for small functions, especially those taking lambdas as parameters.
Why especially lambdas?
Because it avoids creating an object for the lambda at runtime. And there's a cool side effect, smart casts. If a lambda captures a variable and is passed to an inline function, the compiler often knows the lambda will be called immediately. That's the implicit calls-in-place contract, and can perform smart casts on that captured variable inside the lambda.
Ah, okay. That improves type checking within lambdas. Interesting. What about operator overloading and fix functions? They make Kotlin code look quite different sometimes.
They can make it very expressive, yeah. Operator overloading lets you define what standard operators like plus a even, or do for your own types.
How do you do that?
You declare a member or extension function with a specific name, like +4 plus a get for, and mark it with the operator keyword.
An infix function.
Infix functions, marked with infix, let you call a function with just one parameter using a more natural syntax, receiver function name argument, like map contains key.
Without the dot in parentheses.
Exactly.
Yeah.
But one small catch. If you're calling an infix function on the current object, you have to write this function name argument explicitly.
Okay. We touched on higher order functions and lambdas quite a bit. Anything more to add there?
Just to really emphasize how central they are to idiomatic Kotlin. Taking functions as parameters, returning them, using lambdas concisely. It enables powerful patterns like functional programming styles, builders, and asynchronous programming with coroutines. We saw fold, as an example, taking a lambda to combine elements. Function references are just another clean way to pass existing functions where a lambda is expected.
Right, it's a core part of the language's feel. Now, contracts and smart casts, how do they make code safer?
Contracts are like extra promises a function makes beyond its type signature. You can declare, for instance, if this function returns true, then this parameter is not null.
And the compiler uses that.
Yes, the compiler trusts that contract and allows smart casts based on it within the scope where the contract applies. So after checking if input.null, the compiler knows input isn't null. Contracts let you encode more complex checks into functions that the compiler can understand for smarter analysis.
What happens if you put the check in a separate function without a contract?
You might lose the smart cast. The compiler might not know the implications of that helper function call. Contracts make it explicit.
Okay. And smartcasts work in Lambdas now, too.
Yes, with improvements.
Mhm.
If a local var is captured by a lambda, but it's only potentially modified before the lambda is defined or passed, the compiler can often still smartcast it inside the lambda, which is very helpful.
It really feels like Kotlin is constantly evolving. Let's talk about some of those recent updates. What are the highlights from the newer versions, say Kotlin 2.1.20?
Okay, 2.1.20. A big theme there was enhancing multi-platform support. They introduced common atomic types in kotlin.concurrent.atomics.
For thread safety across platforms.
Exactly. Makes writing concurrent code that worked everywhere easier. Also, improvements for UUIDs, better parsing of different formats, new formatting options, and new time tracking stuff with instant end duration.
Handy utilities.
Yeah.
Anything else?
For Compose users, some relaxed restrictions on @composable functions and source info included by default in the Gradle plugin, good for debugging,
Right.
and a neat language feature. You can now use break and continue non-locally within Lambdas passed to inline functions, more control flow options.
Interesting.
Oh, and for web devs, the browser APIs move to a standalone Kotlin's browser library, part of a bigger push towards standard JS interoperability.
Okay, quite a bit in 2.1.20. What about Kotlin 2.0.20?
2.0.20 continued the Gradle improvements, aligning Java test fixtures dependency handling with Gradle itself.
Consistency again.
Yep. Some Compose fixes, including one for unnecessary recompositions that slipped into 2.0.0, also fixed a bug with increment-decrement operators not tracking types correctly.
Good catches.
A bigger architectural thing, the K2 compiler redesign enforces stricter separation between common and platform source sets in multi-platform. Affects how you structure expectactual sometimes.
Okay, something for multi-platform devs to note.
And for WASM.js targets, stable
Yeah.
support for catching JS exceptions, JS exception, a new exception handling proposal for WASM, and production WASM builds get optimized by default using binarian for smaller, faster code.
WASM's getting serious.
Definitely. Plus, named exports and unsigned primitive types support landed for @JS exported WASM functions, improving JS interop.
So Kotlin 2.0.0 itself was big for WASM then.
Yeah, 2.0.0 was the release that officially brought in those named exports and unsigned type support for @JS export in WASM, key steps for better JavaScript integration.
Okay, going back a bit further, Kotlin 1.9 in point 2 and 1.9.6.
1.9.0 mostly involved the Kotlin native distributions starting to be published to Maven Central by default. Easier dependency management, though you could opt out.
Okay, infrastructure stuff.
And
1.9.0.
1.9.0 gave us a preview of a custom memory allocator for Kotlin native, potential performance improvements there. The @volatile annotation became stable in common code, which is important for multi-platform concurrency.
Add volatile for shared state.
Exactly. And you could opt in to use the Kotlin 1.9 language version features in Gradle if you wanted to try them early.
Makes sense. How about Kotlin 1.8.2?
1.8.20. K2 compiler got alpha support in Kotlin serialization, some changes to Kotlin native targets, and the CocoaPods plugin for iOS. Big one. The Kotlin.js IR compiler backend became stable, and the old one was deprecated. Incremental compilation for JS was enabled by default, huge win for JS build times.
So JS development got a boost.
And that precise backup of Gradle compilation outputs we mentioned earlier also landed here, improving incremental build reliability.
What were the key things in 1.7.2 and 1.7.0?
1.7.0. JVM IR backend became default for capped stub generation, mostly internal, better performance compatibility, and the new JVM incremental compilation became default in Gradle.
Okay, and 1.7.0?
1.7.0 had that big rework of incremental compilation for cross-module changes, compatible with Gradle build cache, huge build speed improvements potentially.
Nice.
Also, min, max, etc. came back with non-nullable return types, making Kunk safer. The or null versions still exist, of course.
Did it have both?
New matchat function for rejects, extended support for older language API versions, the build reports we discussed earlier, and support for JS import statements in Kotlin.js, plus setting envars for JS tests.
Kotlin.js getting more mature there too. Let's go back to the 1.6.x and 1.5.x timeframe. Any major milestones?
Okay, 1.6.0 made the hierarchical project structure default for new multi-platform projects, better code sharing organization.
Right. The hierarchy helps manage shared code.
1.6.0 gave a preview of the new Kotlin native memory manager, a major architectural shift. Also, performance bumps for native compilation and runtime. Collection builders, build list, build set, build map became stable.
Collection builders are handy.
Very. And warnings for non-exhaustive when on sealed types booleans became default, pushing towards safer code. These are planned to become errors later.
Good warning. 1.5.30.
1.5.30. Type inference improved for recursive generic types. Ability to use custom C interop libraries and shared native code was added, behind a flag initially.
Interop improvement. And 1.5.0 itself.
1.5.0. Deprecated at JVM default in old modes. Better handling of Java nullability annotations. Stable support for JVM records opt-in. And experimental sealed interfaces were introduced.
Sealed interfaces started there. What about the 1.4.x series? It seems like 1.4.0 was a big one.
Yeah, 1.4.0 was massive. Named arguments could appear anywhere in the argument list. Trailing commas allowed in more places. Type annotations, JS platform improvements,
Lots of quality of life stuff.
and standard library additions. On each indexed, flat map index, the or null variants like random or null, conversions between shari byte array and string, decode tail to a string, etc.
Okay.
Raydic, new string builder extensions,
Wow.
plus scripting RDPL improvements, contracts for static analysis, better smartcasts and lambdas, repeat. For strings, tons of new collection functions, chunked, windowed, sliding, shuffled, destructuring in lambdas, inline extension properties, local delegated properties. Phew.
That was a huge release. Anything notable from 1.4.30, 1.4.20?
1.4.30 had the sealed interfaces prototype and unsigned type serialization. 1.4.20 added experimental java.neo.file, path extensions, and improved string.replace performance.
Way back in 1.3. Any deprecations worth remembering?
Yeah. 1.3 deprecated some inheritance pattern that caused conflicts, nested types in enums, and using single-named args for varargs, pushing the spread operator instead.
Okay, that's an amazing history lesson on Kotlin's evolution.
Yeah.
Let's pivot now to Kotlin Multi-Platform, KMP. Seems like a really hot area.
Absolutely. KMP is a really powerful way to share code. You can write logic once and run it on Android, iOS, JVM servers, web, JS WASM, even native desktops.
And there are tools to help with this?
Definitely. Libraries like Creator for networking and SQLite for databases are built with multi-platform in mind. The community is super active too. Slack, Stack Overflow, you name it.
Is it getting mainstream adoption?
It's growing fast. Google fully endorses Kotlin for Android, and that's often the entry point for teams starting with KMP.
So how does the code sharing actually work, especially when you need platform features?
Well, KMP has great interoperability. You can easily call C libraries or Swift Objective-C code when needed. Kotlin Native compiles your Kotlin to native binaries, dynamic libraries, or even Apple frameworks for direct use.
How do you organize the shared versus platform code?
You use that hierarchical structure we mentioned. It lets you define source sets that are shared between, say, just iOS and macOS, or all native targets, or everything. Libraries can also use this to provide APIs for specific target groups.
And the expect actual keywords are key here.
Exactly. That's the core mechanism.
Yeah.
In your common code shared source set, you declare something with expect, maybe an expect class HTTP client.
Like an interface definition almost?
Sort of, yeah. It declares the API you expect each platform to provide. Then, in your platform-specific source sets, like Android main or iOS main, you provide the actual implementation, actual class HTTP client, Android networking code.
So the common code uses the expect version, and the build system wires it to the right actual at compile time.
Precisely. This works for classes, functions, properties, type aliases, even annotations and enum entries. You can even have extra constants in an actual enum. And you can use platform types in actual annotations, like a JXB annotation on the JVM actual.
What if you need to use an existing C or Objective-C library from common code?
That's where Synerop comes in. You create a .def file describing the Objective-C headers, libraries, etc. Synerop generates Kotlin bindings you can call from your Kotlin native code, even shared native code if you enable commonization for it.
You just bundle pre-built native libs?
Yep, you can add pre-built .a or .so files to your Kotlin native project too.
And for iOS, integrating with Xcode.
You configure your binaries.framework block in Gradle correctly, then add a run script phase in Xcode that calls a Gradle task, like embed inside Apple framework for Xcode to build and embed your Kotlin framework. You can manage framework settings like bundle ID via Gradle too.
What about publishing a multi-platform library for others to use?
You use the standard Maven Publish Gradle plugin. Define your group version repositories. The Kotlin plugin helps create publications for all your targets automatically. Compiler options can be set at various levels: project, target, compilation unit. Dependencies can be declared in a top-level block for all platforms or in specific source set blocks.
What about iOS specifics, like CocoaPods?
KMP has good CocoaPods integration via a Gradle plugin. You add the plugin, define dependencies in a pod file, sync it with Gradle. You can even use @shouldRefine in Swift to make the generated Objective-C headers more Swift-friendly.
Add should refine in Swift.
Yeah, it helps bridge some gaps, making the API feel more natural in Swift. Though complex generic constraints from Kotlin might not translate perfectly to Objective-C Swift, and don't forget Apple's privacy manifest requirements if your KMP code uses certain sensitive APIs on iOS.
Right, platform requirements. Okay, let's switch to another exciting target. Kotlin WebAssembly.
Kotlin WASM, yeah. Compiling Kotlin to WebAssembly, it's still evolving but shows great performance potential, often faster than JS, sometimes nearing JVM native speeds for heavy computation.
What do browsers need to run it?
They need support for the WebAssembly garbage collection, WASM and GC, and exception handling proposals. Support is rolling out across major browsers now.
What should developers know when starting with WASM?
Well, you can enable incremental compilation for faster dev builds. Kotlin.incremental.wasm true. Remember, the browser APIs are now in Kotlin's browser.
Okay.
You can catch JS exceptions using JS exception, especially with the -x wasm attached JS exception compiler flag. You can depend on NPM packages using the NPM function in Gradle dependencies.
Texting.
You test Kotlin JS and thus WASM browser code using Karma configured in Gradle. For production builds, dead code elimination, DCE, is crucial for size.
DCE.
It removes unused Kotlin code. It's automatic in production. JS WASM builds via the IR compiler, but you can configure or disable it. When interacting with JavaScript, use the external modifier for JS declarations and be mindful that properties and external interfaces might need to be var in Kotlin. Companion object members of external classes are accessed directly on the class type.
Got it. Let's move to Kotlin native specifics, memory management, and interop. How is memory handled?
It uses automatic garbage collection now, similar to the JVM. Object reclamation happens during GC cycles.
Any gotchas, especially with Objective-C interop?
Retain cycles. If you have cycles involving both Kotlin and Objective-C objects holding strong references to each other, you can get memory leaks. You need to use weak or unowned references appropriately in those cases, just like in pure Swift Objective-C.
Has the memory manager changed recently?
Yes. There was a major shift to a new memory manager. Migrating might involve removing old things like @shared immutable or freezable atomic reference, use atomic reference now, and exceptions like freezing exception are gone.
Tips for faster native compilation.
Use the latest Kotlin version. Ensure a good build environment, enough RAM, SSD. You can also enable GC pause tracking with a compiler flag or disable parallel mark phase if needed for debugging.
How does native interop with C work?
Primarily through Cinerop, as we mentioned. You create a .def file pointing to C headers and libraries. Cinerop generates Kotlin bindings.
How are C types mapped?
Structs and unions map to Kotlin class objects. Primitives map naturally. Passing data often involves pinning memory, so the GC doesn't move it while C is using it, or using functions like decotostring. C function pointers have a corresponding type in Kotlin native too.
And interop with Java for JVM targets.
That's generally very smooth. Calling Java from Kotlin feels natural. Kotlin understands Java types, including nullability if JetBrains annotations are used.
How about Java generics and arrays?
Java generics are mapped, respecting variants where possible. Java arrays become regular Kotlin array types, which are invariant in Kotlin. You can use Java reflection.
Can you customize how Kotlin looks to Java?
Yes, use @JVM name to change the name of a Kotlin function or property as seen from Java. Use @JVM overloads to make Kotlin functions with default arguments callable from Java easily by generating overloaded versions.
And calling Kotlin from Java.
Also straightforward, properties become getter, setter methods, etc. It's designed to be seamless.
Kotlin's standard library seems packed with useful stuff.
Yeah.
Any particular highlights or recent additions we should recap?
Definitely. We mentioned the 2.1.2 experimental additions, common atomics, better UID support, instant duration time tracking.
Right.
Going back, 1.6.0 stabilized the collection builders, build map, build list, build set, which are now also serializable. 1.4.20 added experimental java.enio.file path extensions and sped up string.replace.
1.4.0 was huge for the standard library.
Yeah, 1.4.0 brought on each index, flat map index, the OR-null variants, share by array string conversions, ORDEC, new string builder functions. 1.7.0 reintroduced min-max with non-null returns and added match out for rejects. It's constantly growing with useful utilities.
We've covered a massive amount. Before we wrap up, any other standout Kotlin features we should quickly touch on? The things that really define the language.
Sure, quick rundown. Extension functions adding functionality without modifying classes statically. Result.
The feature.
Default arguments and name parameters, huge for readability and API design. Inline classes like type aliases, but type-safe potential performance wins. Companion objects for factory methods, constants, static-like members, can implement interfaces.
Right.
Tail recursion optimization, tailright keyword, to prevent stack overflows in recursive functions. Type projections, in-out, and variants essential for flexible generics. Annotations and reflection for metaprogramming. Standard try-catch, finally, plus the use function for resource management. Coroutines for async programming, suspend. Basic syntax like expressions versus statements. Idiomatic coding conventions.
What about comparisons to Java?
Kotlin's handling of strings, collections, read-only versus mutable rich API, and especially null safety are major advantages over traditional Java. Regex support is good, collection covariance, powerful filtering associating functions, null safety is built in, a huge win.
Neither of it.
Reading input via Java scanner is easy, operator overloading for custom types, range expressions, destructuring declarations to unpack objects, and powerful type inference reducing boilerplate.
Wow, okay. That's an incredible tour through Kotlin, all drawn from that source material.
Yeah.
We definitely aim for that quick yet thorough understanding, and hopefully you, our listener, had some aha moments along the way.
Yeah, we really covered a lot, from the compiler and Gradle efficiency, through the expressive core language and syntax, the exciting multi-platform and WASM developments, Kotlin native's nuances, and that rich standard library. It's quite a landscape.
We hope this deep dive gives you a really solid foundation. And maybe it sparks some curiosity to explore specific areas further. We definitely encourage digging into sample projects or the community resources mentioned in the docs.
Absolutely. And maybe leave you with a thought. As Kotlin keeps evolving so quickly, how might all these features, the compiler smarts, the multi-platform reach, the language flexibility, how might they collectively reshape how we build software across all these different platforms in the future?
A good question to ponder. Something to think about as you continue your own Kotlin journey.